Welcome. So, let us start, as I said, with the free energy of mixing expression that we discussed in the last section, which was derived in the previous module. So, the free energy of mixing, as you can see, is written as omega xb 1 minus xb plus RT xb ln xb plus 1 minus xb ln 1 minus xb. If you remember, in the first module, when I derived this expression, I wrote this as omega xa into 1 minus xa plus RT xa log xa plus 1 minus xa log 1 minus xa. As you can see, these two expressions are the same. This is because xa plus xb is equal to 1. That is because the total number of sites n is occupied by Na and Nb atoms, and Na plus Nb adds up to 1. So, if you have Na plus Nb, which is equal to n, divided by n, that will be equal to 1. So, Na by n, which we defined as xa, plus Nb by n, which we defined as xb, is equal to 1. So, thus we have this symmetry between xa and xb. Suppose if you want to write everything in terms of xb, you can write it is xb into 1 minus xb plus RT xb ln xb plus 1 minus xb ln 1 minus xb. Suppose if I start replacing, xb is nothing but 1 minus xa, 1 minus xb is nothing but xa, plus similarly xb is 1 minus xa and 1 minus xb is xa. So, you can write it. So, already you can see that this expression is symmetric with respect to xa xb. And typically the reason why I wrote it as xb is as follows. Typical phase diagrams, for example, if you take copper nickel phase diagram, so then you have pure copper here, pure nickel here. So, the x axis of the phase diagram basically gives you the, which is denoted typically as x, it is basically the composition of nickel. Okay. So, and if you decide to call this kind of phase diagram by a generic A and B type of atoms, then the composition axis is basically nothing but xb. So, that is the reason why most of the times the expressions are written in terms of xb, but they can equally well be written in terms of xa. In other words, I mean copper nickel phase diagram, you can start with pure nickel and go to pure copper, or you can start with pure copper and you can go to pure nickel, it does not make any difference. Okay. So, in the regular solution model, on top of it, the expressions themselves are also symmetric with respect to using xa and xb. So, they are interchangeable and you get the same expression. So, let us consider these terms one by one. So, let me take the free energy of mixing. It consists of two parts, the enthalpy of mixing and entropy of mixing. If you look at these terms individually, so let us take a look at it. Delta G mix is nothing but omega xb 1 minus xb plus RT xb log xb plus 1 minus xb log 1 minus xb. By the way, irrespective of whether I call it log or ln, it is a logarithm to the base e, and we typically do not use logarithm to the base 10. So, I keep calling it sometimes as log, sometimes as ln, but it is the same. Okay. So, by default when I say logarithm, I mean to the base e. Alright. So, let us take a look at this expression. So, this is nothing but delta H mix. Okay. So, if you try to plot this quantity, then as a function of composition, which is given by xb, so this is a parabola, right, and if omega is greater than 0, so it is a parabola that looks like that. If omega is less than 0, it is a parabola that looks like this. In a similar fashion, you can try to plot this quantity. So, this is delta H mix plot, and I can also plot delta S mix. Remember, like we discussed yesterday in the previous module, xb is less than 1. So, logarithm of xb is going to be a negative quantity and the rest of the terms here are positive. So, this quantity is always negative, which means depending on the temperature, it will only tell you how deep this parabola is. This is also looking like a parabola, right. This is also a curve which is symmetric about the central point, and it looks like this. So, this is at some temperature T1, this is at some temperature T2, and you can see that T2 is greater than T1. So, delta H mix always is going to give you negative quantities, and only delta H mix can give you positive or negative depending on whether omega is greater than 0 or omega is less than 0. Now, let us take a temperature T which is high, so that you will see only the entropy of mixing term to be dominant. Okay. So, in terms of this plot, how does it look like? So, it looks like this. Okay. So, my delta H mix could be like this, my delta H mix could be like this, it does not matter. My delta S mix is like this. Okay. So, this is delta S mix, this is delta H mix with omega less than 0, this is delta H mix with omega greater than 0. Now, let us find out what happens if you add and you make the delta G mix, because in this case both add up. So, you will get something that looks like that. Okay, it should be symmetric. So, this is delta G mix, in the case omega is less than 0, and in the other case of course, this much will be taken off. So, it will come something like this, okay, because this quantity is positive, you are adding to this. So, it will go somewhere here. So, this is the case where you have delta G mix where omega is greater than 0. So, in other words, we are talking about a case, this is T delta S mix by the way, because T term is already there. So, we are talking about a temperature T which is large enough that the most important contribution is coming from the entropy of mixing. Okay. So, it does not matter whether your omega is greater than 0 or omega is less than 0, because the temperature is very high, that is the dominant term, and you always get your free energy versus composition diagram, something like this, right. This is the composition axis, this is the XB axis. On the other hand, let us consider a case where the temperature is not very high. Okay. So, I have a delta S mix and a temperature such that it is something like this. Okay. So, this is at some T delta S mix. Okay. Now, I am going to consider two cases, one in which the delta H mix is also negative. So, this is delta H mix. In the other case that I am going to consider, remember this is the XB axis. So, I have the XB axis and I have T delta S mix again, which is here at the same temperature. But now, my delta H mix is not negative, but it is positive. Okay. So, this is my delta H mix, okay, because this omega is greater than 0, whereas this omega is less than 0. So, as you can see, in this case again we find that if you add delta H mix plus RT delta S mix, you are going to get something like this. On the other hand, when you have these two terms at the extreme ends where XB is 0 or XB is 1, the entropy term is still going to dominate, because very small composition changes can give rise to huge changes in entropy. You can imagine it like this. Suppose if you have one atom and you have about 10 power 23 sites, and this one atom can occupy about 10 power 23 different sites. So, the total number of available configurations becomes so large that that becomes very dominant. So, at these extreme ends, either you have pure B in which you are putting very small a, and or you have pure A in which you are putting very small b, this is always dominant. And so, this will always dominate at the lower compositions, but somewhere in the middle, because the delta H mix will start dominating, it will become like this, and again it will become like this. In other words, in the case when delta H mix is greater than 0, we get to some interesting composition versus free energy curve. Is remember the free energy that we are talking about is a free energy of mixing. Okay. So, we are only talking about free energy of mixing. So, in cases where the temperature is very high, you always have this kind of shape. In cases where temperature is not so high, that delta H mix can still dominate, then depending on the sign of delta H mix, you might get a parabola or you might get a curve which has 2 minima and 1 maxima in a binary alloy. Okay. So, these kind of systems are known as phase separating systems, and we will discuss this a little bit more detail later. And this is phase separating system because remember delta H mix greater than 0 meant this omega greater than 0, and omega was nothing but EAB minus half of EAA plus EBB. Now, this quantity is positive, means that AB bonds are costlier as compared to on the average making AA and BB bonds. So, if you have 2 AB bonds, you will break them and you will make AA bonds and BB bonds out of it, and in the process you will reduce the internal energy, which will lead to in turn reduction in free energy. So, it is always favorable in this case for the system to phase separate, that is become pure in A and pure in B separated out. On the other hand, in this case when this omega is negative, that means EAB minus half of EAA plus EBB is negative. That means the AB bond energy is lesser than on the average AA-BB bond. So, if you have AA-BB bonds, the system will break them and make one AB bond. And this is the case that we discussed. So, at very low temperatures, such systems undergo what is known as ordering. So, this is ordering. Remember that this is only at low temperature, this is phase separation, again only at low temperature. At high temperature, all the systems are dominated by entropy, and so they will all become random solid solution. But at low temperatures, the systems might become ordered or phase separated, and they will become a random solid solution only if omega is 0, and if omega is not 0, there is always a temperature at which you will find that the system either prefers to order or prefers to phase separate. Okay. So, we will discuss this case in a little bit more of detail with specific emphasis on phase separation in this module little while later. Thank you.